rate of change at a local maximum or minimum. So you studied these local maximum and minimums in your functions course. So in advanced functions, as you kind of get into rates of change, I thought I would make this kind of short little video to remind you, what happens at these maximum or minimums now from the viewpoint of rate of change. So I guess technically instantaneous rate of change, okay? So at a particular maximum or minimum. Now, so let's consider an example, right? And it doesn't matter what you take, but I guess, I kind of picked one that has a maximum or minimum. If you think of your quadratics, so a quadratic, so either parabola looking up or looking down, you know that there's a maximum or a minimum depending on how it's looking. Okay, now in some other polynomials, so let's say like this one is of order 3, you can actually have something where it has local maximum or minimums, okay, where there's actually a change of rate happening. And as you have this change of rate, it's very easy to be able to see what happens, okay, at that local maximum or minimum with respect to the instantaneous rate of change. So I'm going to take, this right here, function, so x cubed plus 3x squared plus 2. So, it's a nice function. There isn't anything crazy happening because it's a polynomial. The domain basically is the entire real number line. Okay, and then the range in this case also is the entire thing. So we don't have anything kind of funky happening. But these maximum and minimums, I do want to kind of give it and describe them to you from the viewpoint of the instantaneous rate of change. So, here's our kind of definition of the instantaneous rate of change. So, your output, so the change in your output with respect to the change of your input, and we can summarize it in this way where our function, at a particular point A, okay, and then it's being kind of adjusted around that point A by this h, okay, and then h is approaching 0, okay, both on the positive and negative side, but it's getting smaller and smaller and smaller, all right? So we obviously would have to kind of know where these maximum or minimums are happening. Now, we can do that in many different ways, right? So one of them is, we can kind of graph this thing and then see what happens, right? So for this particular item, before I kind of get into the graph and we're going to see where the maximum and minimum actually happens, I do want to talk to you about, just the gist, okay, of the instantaneous rate of change at these points. So this function actually is going to look kind of like this. Okay, I'm going to kind of draw it out like that. So it takes off in here, takes down in there. But you see here that you have a local. So here's a local maximum at this point. So that's the max. All right. So locally, so around that area, it is, okay, the maximum point. And then this point right here, okay, so locally, so again, around some area like that, okay, for a particular, domain, okay, this would be the minimum. Now, if you're thinking of the viewpoint of instantaneous rates of change, so we can tie it back into tangent, right? So what is happening, okay, if we wanted to put a tangent near here, you would very quickly notice, you'd be like, well, that's interesting. So notice right here, so if I put a tangent, so it's kind of very steep, positive, okay, but as I get closer to this maximum, so notice it starts to level off. And you might probably think and notice that, like, if you pass it, then it starts to kind of slope down, right? So around that point of the maximum, it shouldn't surprise you, okay, and we can kind of take a guess that at that point, so at this point, let's say this was your point A, okay, and this is your max, all right, so that's your max. The actual tangent, so the instantaneous rate of change at that point is 0, okay, and you can see that because of the slope is changing from being steep, less steep, less steep, then it has to flatten at some point so that it changes direction. Now, on the other side, so on here, this must also be true, right? Like if you're going to go on a minimum, so notice it's steep and then it just kind of changes direction afterwards. So I'm going to put another one here. And indeed, what is going to happen is that at this minimum, okay, it's going to have a flat Okay, so the instantaneous rate of change, so the slope is basically 0. So at that point, so if this is your A minimum, okay, you're going to notice that if we would be calculating, okay, this instantaneous rate of change, so this entire thing right here, we would substitute it back in, you know, we would get 0. Now, what I'm going to do, okay, is we're going to try to graph this thing, find what this A max and A min is, so what's the value of X at the maximum and the value of A at the minimum, and then we're going to try to substitute it back in. I mean, I'll speed up the calculation, but I'll show you that it will give us an instantaneous rate of 0. All right, so here it is, because I kind of cheated and I graphed it beforehand. So, you know, we have, so x cubed plus 3x squared plus 2. And so what we have is we basically have, so we have 1 point right there. So notice that it's at -2. Now the value for y is 6, okay, at that point. And then here, okay, so at this point it's at 0, and the value for y is 2. So that's what we have. So that's what we have, those changes. So -2, okay, and at 0. So now let's go back in here, and we'll pick one of them, and then you can try the other one. So for example, let's say max. So this happened at -2. All right, so that's what we had. And now if we would take our actual, so if I'm going to take this whole thing right here, okay, I'm going to copy it, paste it down, and now let's substitute everything in here with, you know, our function. So here's our function. So I'm going to copy this just so that I have it on the side. Paste. Okay, I'm going to make it smaller. Okay, and let me get to work. Okay, so I'm going to be substituting this negative, okay, right here, okay, and right here. The h I'm going to make smaller and smaller, so I want to get in kind of a algebraic expression, okay, for this instantaneous rate of change at that -2. And then we're going to find it. So we're going to substitute h, which is very tiny, okay, positive and very tiny, negative. We'll take the average of the two, so it's going to approximate our instantaneous rate of change, and you'll see that it's going to be 0. All right? Okay, let me do the work. All right, so I was just kind of manipulating all of this stuff. Okay, so now that so I kind of simplified it. Okay, so we canceled things out, collected things. Okay, so what we were doing is basically this. Now we can substitute, you know, h as small as possible. You know, so even if we take it, you know, you can make it as small as possible. But you can see here that as h tends towards 0, so that it's getting smaller and smaller and smaller, you know, this whole thing, because it's h squared minus 3h, is going to get smaller and smaller and smaller. So basically it's going to go to 0, right? So that's what's going to happen to that particular slope. Okay, so if I substitute this in, let's say for that, you know, if I would get this, all right, and then this. So in this particular case, you know, this is going to be very tiny, okay, and then this, okay, is going, because I'm squaring this, so this is going to go more towards, okay, so 0.003, all right, plus that little tiny amount, okay, which is going to be, I guess, so something approximately there, all right. So this becomes smaller and smaller. And then on the negative side, so if you substitute this for the negative, because this is positive, right, and we want h from both sides, positive and negative, so it would have been, okay, so again squared plus, okay, and then this is going to be 3 times negative 0.001. All right, so now this is going to be negative, okay, so you're going to get this 0.003, and then this, you know, it's going to be plus, okay, so this is going to be 0.001, plus 0, 0, 0, 0, 0, 1. Okay, so it's going to be very tiny. Okay, so within here, so minus 0.00, I guess you're adding this up. There's going to be 2 and then 9, 9, 9, I guess, 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. So approximately there. All right, so you have these two. Now, if we average those out, so, if we add it up together, so notice one is positive, one is negative, and you add it up, it's basically going to be, 0.00000, okay, and so on divided by 2, which is going to make it even smaller. So the slope, and as you make h smaller and smaller, this is going to tend towards 0, which is exactly what these local maximum and minimums, or any maximum or minimum, scale on graphs, because of the changes, the slope at that point is going to be 0. So the instantaneous slope at a maximum or minimum is actually 0. All right, so that's what I wanted to point out in this video. I showed this an example, kind of worked it out. Working it out is annoying, I'm sure, until you get to calculus, which especially for polynomials, then it's kind of easy. But until that point, they probably will make you do this in advanced functions. Just remember that local maximum and minimums have an instantaneous rate of change of 0 at those points. All right, thanks for watching. See you in a future video. Bye, everybody.